Welcome to the third part of Lesson 8, which is our usual applied lesson. So what we will do now is to play a little bit with R and RStudio to better understand the different topics we have covered so far. For example, we will see one of the ways in which we can estimate the theta parameter, the extremal index, and we will say something more about records and how they can be used as an additional plot together with all the other plots we have already considered in extreme value theory to better understand our data, especially when understanding whether the data are i.i.d. or not is pivotal, is essential for our analysis. Now, let's start by saying something about the extremal index and also records. We will use the dataset BMW that we have considered last time in our first live class. And what I want to show you is what we can say from a time series point of view when we focus on maxima with respect to that time series that you remember contains the daily log returns of the BMW share price from 1973 to 1996. Now, the data are obviously stored in the heavier library that we will need, so we upload our library and we use our BMW data. Okay, so if you want to know more about this, you just type question mark and then you can find all the information about this data. Now, if you remember what we have said in our live class is that this data set shows some mild tails both for the returns and the losses. In particular, if we focus on losses, we find out that these tails that belong to the Frechet maximum domain of attraction because the psi parameter that we compute is positive and significant. Remember that the fact that psi is significant is pivotal for us, yet the value that we get for the psi parameter in the vicinity of 0.2 indicates that for sure the third moment is finite and possibly also the fourth. So in a sense, we are not playing with extremely fat tails. Now, the question that we can ask ourselves is, we have modeled losses and returns as if they were coming from an i.i.d. collection of observations. But we know that these are daily returns, okay? So they form a proper time series. And the idea is, what happens if we take into consideration this fact? So the fact that we are not playing with i.i.d. observations, but rather with a time series. In order to do that, what we have to do is to estimate the extremal index. But in order to understand if we can estimate the extremal index, what we have to verify is that our time series is a time series for which we can assume the deconditions to hold. Now, there are many ways in which we can do this. Some are more advanced, some are a little bit less advanced. So we will consider something in this second category. For the more advanced techniques, obviously we have to perform time series analysis, for example, verify that our time series model is something like an ARMA, an ARIMA, a stationary model, and then we can also perform tests to verify the deconditions, but we do not enter into the details. What I want to discuss with you is the use of a nice quantity in extreme value theory, that is to say, records. Now, what are records? Records are nothing more than the same type of things that you consider in spores. Okay, so imagine that we have a collection x1, xn of observations. What we know is that we can always define the quantity mn to be the nth partial maximum. Okay? Now, by definition, observation x1 coincides with m1. Okay, the first observation is by definition the first partial maximum. Now, one of the observations, in particular a quantity xn, is a record for our dataset if we have that xn is larger than mn minus 1. So, when we observe xn, xn is a record if trivially is the biggest value observed so far. So, once again, trivially we have that x1 is a record. So we have that x1 is a partial maximum and a record. But for all n, small n larger than 2, what we have is that not necessarily we have that x2 is a partial maximum and a record. And the same for x3, x4, x5, and so on. Now, once we have given this very simple definition of record, that I repeat is an observation such that it is larger than the previous partial maximum, we can identify the so-called record counting process. And this process is defined as follows. N1 is equal to 1. Okay? Why? Because the first observation, x1, is equal to the partial maximum and the first record. Then, for all small n larger than equal to 2, as you can read here, we have that the quantity nn is equal to 1 plus the sum for k from 2 to n of the indicator of the event that our observation is actually a record. Okay, so the process n is nothing more than a process that counts the number of records in our observations. Now, this counting process is extremely useful for us. In fact, Gumbel observed that if our sequence x1, x2, xn is made of i.i.d. observations, then we can obtain that the expected value of the number of records, so the expected value of nn, is equal to the sum for k from 1 to n of 1 over k. And for what concerns the variance of the variable nn, this variance is exactly the quantity that you see on your screen. So it's the sum over k from 1 to n of 1 over k minus 1 over k squared. The proof of this is extremely simple, so it's just a matter of taking into consideration the definition of the process that we have given and the properties of the maxima. But if you're interested, you also find the proof in the book by Embrechts, Mikosch, and Kluppelberg. Now, a very interesting thing that we have to observe is the following. The expected value of the quantity nn is of the order log of n, for n growing towards infinity. If you want, we can show that actually nn rescaled by the log of n tends to a quantity gamma for n growing towards infinity. And this gamma is nothing more than the Euler's constant. So the constant equal to 0.5772 and so on. So if you want, you can also rewrite everything and state the following. The expected number of records in a sample of size small n for n growing towards infinity, it's more or less the log of n plus gamma, where gamma is the Euler constant. Now, if you don't believe what I just said you, we can try to verify if this is true via some simple simulations. And again, if you want all the theoretical details, I refer you to the book by Embrechts, Kluppelberg, and Mikosch or even to the original book, Statistics of Extremes by Gambo. Now, imagine that we consider a sample which is made of i.i.d. observations, and we consider 10,000 observations. All these observations are drawn from a Pareto of parameter 2. So it's a standard Pareto with minimum value 1 and shape parameter equal to 2. So it's a Pareto with a relatively fat tail, because remember that if the alpha parameter of our Pareto is 2 or more, we have the existence of the variance, but here we are on the borderline situation. Okay, so we can use the library vegan, which is a nice library for generating random variables and performing other type of statistical analysis. I set the seed so you can reproduce exactly my result, and then I generate my sample of 10,000 observation from a Pareto of shape 2 and minimum value 1. After that, we compute the partial maxima, okay, using the CAMMAX function of R. And we can then simply define our record counting process by setting the first value equal to 1, because remember, n1 is equal to 1, as we have stated here, okay? And for the rest, we just apply this second formula. So for I, from 2 to the length of x, we just verify the condition such that a given observation is a record. And if this condition is satisfied, we increase the number of records we have observed. Now, what happens if we run this code? We find out that our observation, let me comment here because I find it. Okay, apply. So good. So if we run our simulation, we find that the number of records we find in the data is equal to 9. So we observe 9 records. Now, what is the number of records that we predict if we use the empirical formula that you see now here on your screen? So the expected number of records is equal more or less to the natural logarithm of n plus gamma. Remember that in R, log is the natural logarithm, so that would be ln. But in the R notation, log is the natural logarithm. So it's more consistent with the European rather than the American way of expressing the logarithm. So for us, log is the natural logarithm. So if we apply the formula, we take the natural logarithm of n, that for us is 10,000 observations, plus our Euler constant. If you want R to compute this, you can use the d gamma function, okay? Otherwise, you just simply write down an approximation of the Euler's constant. And if you use this formula, what you get is that the value we get is 9.78, okay? Now, 9 and 9.78 are rather close. But one could ask himself or herself if this is just a matter of chance, okay? Because obviously we are just generating one sample of 10,000 observations. So what we can do, we can generate a Monte Carlo experiment in which we generate 10,000 samples, each one of 10,000 observations, all i.i.d. according to our Pareto 2 distribution. If you want, you can change the distribution and you will see that nevertheless the result holds. Okay, so I now create a vector R in which I will store for each one of the different Monte Carlo experiments the number of records we find. So we have first for loop for j in 1 10,000, and within this loop we just replicate what we have done before. Okay, So we create our quantity R, and now in this vector we have the number of records in the different 10,000 experiment that we have performed using Monte Carlo. This code here is everything but an efficient code. If you want, you can improve it. But I think that written in this way, it is quite simple to understand what is happening. Now, if our approximation is correct, as you can read on your screen, we expect an average of 9.8 records in our data, because this is what we observe using the empirical formula. So 9.78, we round to 9.8. And the standard deviation that you can easily obtain from this quantity here, we have that should be around 2.8. Okay? Now, let's do the following. We compute the average of R, we compute the standard deviation of R, and we then look at the histogram. Okay, so let's do that. We find out that the expected number of records in the different samples is 9.74, which is actually very close to our 9.78, and if we round to our 9.8. And for what concerns the standard deviation, it was expected to be 2.8, and for us is 2.84. So definitely good. And here you see the histogram. You see that most of the samples satisfy our approximation. Then obviously you have some variability around the expected value, and this variability is consistent with the standard deviation of 2.8. So records do follow this logarithmic behavior when they come from an i.i.d. sample. Now, how can we use this information? We can use this information to create a so-called record plot. A record plot is a plot that, on a log scale, plots the expected number of records in our data with confidence bands, typically 95%, but you can obviously change it if we assume that our observations are i.i.d. So what happens is that in the typical record plot, you observe something like this. You have a line that represents the theoretical behavior of the records in an i.i.d. sequence, of an i.i.d. collection. The first observation, by definition, is a record, and then you have the confidence intervals that here are at the 95% level. Then what do? You can compare this theoretical behavior. So if your data are i.i.d., you would expect the records in the data to be on this line, okay? Consistently with the empirical law discovered by Gumbel. If the data, and here you see the points here, they are taken from our BMW dataset. If the points that you get from your empirical data fall within the confidence intervals, obviously if they are on the line, you can really say it's highly probable that my data are i.i.d. The more the distance increase, but still you are in the confidence interval, you can assume that your series, even if not exactly i.i.d., satisfies the stationarity condition and the d conditions. So in a situation like the one that you see on your plot, you can be somehow satisfied and say, okay, yes, it makes sense to assume that my BMW dataset satisfies the d conditions, so that I can apply the generalized version of the Fisher-Tippett theorem and estimate the extremal index. How? For example, using the block method. If you want to generate this type of plot within the every library, you can use the function records. Okay, so you can do this. You find the similar functions also in other packages like i.i.d. or fxstreams. But one of the every package is very simple. What you see is that it also shows you the records, the expected number, and so on, which is the typical way in which records are studied. If you want, again, I refer you to the book by Embrex and friends. But what is nice for us is that in a plot like this, since our empirical observations are within the confidence bands of the logarithmic progression, then we can say that, okay, so these data are likely not to be exactly i.i.d, which is not a big surprise, it's a time series of daily returns, so it would be quite strange to have i.i.d observations. It would be that essentially our returns constitute some sort of white noise, but we know that does not make any sense. But since we are within the confidence bands, we can assume that the conditions are satisfied. Now, how can we compute the theta? There are different methods in the literature. We have the runs, we have the cluster size, we have the block method. We have briefly considered together the block method. You remember, you divide in block and then you count the number of exceedances over a high threshold within the blocks. You compute the capital K quantity, you compute the capital N quantity, and you relate those quantities with small k and small n, and then you can compute the extremal index. Now, so what can we do? Let's compute the extremal index for BMW using blocks of 100 observations. Okay, you can try with other size if you want. This is a decent size considering the number of observations. Remember that the block size is highly dependent on the number of observations that you have. There is clearly a trade-off. Considering our data set here, what we have is that in our data set we have somehow more or less 6,000 observations. And if we divide by blocks of 100 days, it means that we obtain more or less 60 blocks. So what happens? We do that for the returns and for the losses. For the returns, obviously, we take the time series as it is. For the losses, since we are interested in the maxima, but we are looking at losses here still as negative quantities, we have to switch the sign to get positive quantities for the losses as well. Okay, so and here there is an error, so these are losses. Okay, so what we can do, we can generate our plots, and using this method, you look for the value of the theta parameter of the extremal index that somehow represents some sort of average of the values that you can see here. In principle, you could look for the value for which the plot stabilizes, but if you take the average, typically you are okay. What we get is that we have a value of probably 0.7 for what concerns the returns, and a value of around 0.6 for what concerns the losses. So recalling the interpretation of the theta index, we have that there is a little bit more dependence among the maxima of losses, which is not a big surprise if you want, in terms of also financial economic interpretation of the sentiment of the market, and the fact that typically when things start going bad, then they start also getting worse. And we can essentially try to give a justification of this. If you want a plot which is a little bit easier to interpret, you can use a library which is called fxtremes. That is a library more targeted on the financial analysis, on the analysis of financial data using extreme value theory, but is also a little bit more complicated in some of its parts. So I think that for starting, Avir is much better. But if you use this library, you can use the function xindexes. That essentially gives you a better way of giving an interpretation of the theta parameter. The only thing is that you have to be careful, because if you use this function, so if you look at the returns and the losses, you see that you have three different series. The only interesting series for us is the black one here, like these and these. We can ignore the other two. The other two are the so-called theta 2 and theta 3, that are other ways of estimating the theta parameter using runs or using, for example, the cluster size, the mean cluster size. And the way in which you interpret these parameters is a little bit different. Typically, you look for the value for which the three different methods agree. But if we just restrict our attention on the first method, so the block method, we see that what I told you before, a value around 0.7 makes sense for what concerns the returns, and a value around 0.6 makes sense for what concerns the losses. So what's the interpretation of the theta parameter? It is the following. Once we know that there is a theta which is different from 1, that would correspond to the case of i.i.d. observation, that in the record plots would correspond to seeing these dots not here but rather here on the line, what we have is that we can use the information of theta to get a better grasp of the maxima behavior in our data. Okay, so if you go back to our live class, you will find out that at a certain point we were computing the daily 99.9% valid risk. But nevertheless, it's something that we will see together. We will need to compute, for example, in the market risk assessment under the Basel framework. Okay, so if we consider the 99.9% valid risk of our daily BMW losses, we find out that this value is more or less 0.1. Okay, is a loss of about 10%. Now, this means that on a daily basis, 99.9% of times we will observe losses that are in absolute value smaller than 0.1. The question that we can ask ourselves once we have the theta parameter is the following. What happens if, instead of considering these daily losses, I take a longer time horizon, like 100 days, and I'm interested in knowing what the value 10%, so 0.1009, represents in terms of losses over the 100 days time horizon. Now, if we assume that our observations are i.i.d, then what we have is that the value at 99.9% to the power 100, because we are assuming i.i.d observations, would correspond to more or less a 90% confidence level. Okay, we would have that this value of 0.1 would correspond to a 90% confidence level. If, conversely, we exploit the theta index that we have already just computed and that we saw for losses is around 0.6, we can improve this estimate by taking 0.999 to the power theta n. Okay, so n is still 100, theta is 0.6, so instead of taking everything to the power 100, it is like taking everything to the power 60. Okay, and what we find is that now this value does not represent the 90% valid risk over a 100 days time horizon, but rather the 95 one. Okay, and you see that the difference is quite relevant. So the fact that we have this theta parameter allows us to give a better interpretation of our losses and also possibly give present a better analysis of the potential high losses that we can expect from our data. Okay, so now what I want to do is to briefly, very briefly discuss how we can estimate a Garch 1-1 model using R. The way in which we can estimate arch models is completely the same, so I leave that to you if you are interested. We will use a dataset that is contained in the ASTA package. The ASTA package is quite interesting because it's the uh, companion, you see here, companion package of the book by Shamway and Stoffer that I have suggested you for time series. Uh, and we will use the fgarch package to estimate our Garch 1-1 model. So what we do is we run our package, okay? Now, what happens? We use the dataset GNP of the US gross national product that contains seasonally adjusted quarterly observations from the first quarter of 1947 to the third quarter of 2002. And what we want to model are the growth rates. Okay, so what we have to do once we have uploaded the ASTA package is simply to, okay, yes, sorry, but I'm picky on these kind of things. So we upload our data and then we just compute the growth rates by taking the difference of the logs. Okay, now the time series is what you see here on your screen. So this is our time series of growth rates. Now, as an exercise, I leave to you to verify that if you want to fit a model to this data, for what concerns the model, a simple autoregressive model of order 1 works nicely, but I leave that to you. Now, the question is, once we have performed our analysis and we found out that our autoregressive model of order 1 works decently for our data set, what can we say about the residuals of these time series analysis? Okay, so if you fit the model, these are the parameters you get. You see they are significant, they make sense. We can give nice interpretations, but I leave that, again, I repeat, to you. What I want to focus on are the residuals. So I can take the residuals of my fitting, I can plot the residuals, I can look at the ACF and the PACF. Now, if I do that, I see the following. Okay, for what concerns the time series, this is the time series of the residuals, okay, no big deal. If I look at the ACF, I find out that it seems that I have been able to remove essentially all the dependent structure. Yeah, there are some lags that appear to be possibly close to being significant, but again, I repeat, you always have to consider what happens in between the legs. So here we could say, okay, nothing particularly important. If we look at the PACF, again, this is consistent with the fact that it seems we have removed all the necessary information. But what happens if we square the residuals, which is typically what we want to do to verify if there is something with respect to volatility, so to observe if there is some sort of heteroscedasticity in our data. So we can have the ACF of the squared residuals and the PACF. If we do that, we discover something. We see that for what concerns the ACF, some legs, definitely a number of legs larger than before, are very close to be significant. Some are significant, like this one and this one, but also this one is very close to our dashed line. So remember that the concept of something being significant, so significance depends on the level you choose. So it's not necessarily that you have to use the 95% confidence level with a type 1 error of 5%. You can move to the 90%, you can move to the 99%, so it really depends on you. And when you see a situation like this in which you are very close to the border, I always suggest to try to see what happens if you go further with your analysis, okay? Don't just stop because it seems that here you are not significant. In statistics, when you are close to be significant or close not to be significant, you still have to conclude your analysis because these are the tricky situations. Okay, so what happens if we want to fit a Garch 1-1 model, which is the typical type of model that you would fit in a situation like this. So when you play with GNP, when you play with growth rates in general, when you play with volatility of financial assets, the Garch 1-1, as I told you, is probably the best model because it's simple but powerful. If you want, you can be more advanced, you can introduce other type of models, but if you want to be simple yet rely on a model with nice properties, the Garch 1-1 is a very good candidate. Okay, so let's fit our model. So the model is easily fit by using the Garch fit function, residuals, and then we have the tilde that in R signifies that our residuals follow a Garch 1-1. Okay, if we do that, what we get is the following. So this is, okay, the table representation, but what is more important for us is the R console. So the first window. In the first window, what we get the estimate of mu, we have omega, alpha, beta. Now, in the way in which we have defined our model, what is really interesting for us are omega, alpha, and beta. Now, omega, you remember, is gamma times VL, where VL is the long-run variance. Alpha and beta are the other two parameters that together with the gamma, not gamba, gamba means leg in Italian, so the gamma within omega together with alpha and beta sum to 1 because we are considering a convex linear combination. But what we do here is we have omega and we want, for example, to get out the information about the long-run variance or the long-run volatility. Notice that all parameters, omega, alpha, and beta, are significant, okay? Because if we look at the standard error, if we divide the estimate by the standard error, we see that in absolute value we are out of the -2 interval that very quickly we have used several times in heuristic terms. Okay, so we see that these parameters are significant, and for example, if we are interested in the long-run volatility, what can we do? We can take omega, and we can, that is equal to gamma times the long-run variance, and we can divide omega by 1 minus alpha minus beta. Why? Because alpha plus beta plus lambda sum to 1, so 1 minus alpha minus beta is equal to lambda. And since omega is equal to the long-run variance times gamma, if we divide omega by gamma, we get the long-run variance. And once we have the long-run variance, we can take the square root and we will have the long-run volatility. So if we do that, the value we get is a volatility of 24.5%. And once we have these parameters, we can use these parameters in our formulas that we have seen in the class. We will see in other classes how we can go further into the analysis of these models. Let's say that for the moment we stop here. What I suggest you is to invest a little bit of time understanding what the Garch fit function does, which is not at all difficult. So you are just estimating your Garch model using maximum likelihood, and then you have all your standard parameters with their standard error. Mu is a parameter related to the constant term that in our specification is not particularly important, and nevertheless here it is not even significant. So in a sense it can be ignored in the further modeling of our volatility. Okay, thank you for your attention and see you in our next lesson, whose topic will be market risk. So we will start considering market risk in the so-called Basel framework. So we will see how we can actually try to model market risk losses, and we will discover that the valid risk and the expected shortfall play a major role in the approaches that we can use. And okay, but it's too early for that, so be patient until next time.